Hello everyone. Today we are going to consider discrete logarithm. So when we are going to consider discrete logarithm, it is defined as power of an integer modulo n is known as discrete logarithm. For example, here I have taken y is nothing but a to the power of I mod n. In that case, the index I will or the exponent I will be taken as discrete logarithm of y, okay, to base a. So when we are going to consider discrete logarithm, what we are going to do is we will going to express the I, that is the exponent, uh, which is considered as discrete logarithm. And if you know the value of y and the value of a and n, finding the value of I is hard or infeasible. That is the reason we are going to consider this type of representation in RSA algorithm as well as Diffie-Hellman key exchange. Sorry, it is RSA. In RSA as well as in Diffie-Hellman key exchange, mainly we are going to consider discrete logarithms. So here, suppose if n represents a prime number, let me consider the prime number as 7, and then a represents the primitive root. Okay, so now suppose if a is equal to 2, then what I have to do? I have to generate all the elements 0 to 6, that is 0, 1, 2, 3, 4, 5, 6 using the primitive root. But one thing, we cannot generate 0. So why we cannot generate 0? Product of two numbers is 0 means at least one number must be 0. Since I am using only a primitive root and this primitive root is not equal to 0, as a result I cannot generate 0. So using the primitive root, I need to check whether I can generate all the elements of the group. Okay, so let me consider this. 2 to the power of 1 is 2, and 2 square is 4, and 2 cube is 8, and 2 raised to 4 is 16, 2 raised to 5 is 32, and 2 raised to 6 is 64. For all these value, I need to take mod p, that is mod 7. So when I'm going to consider mod 2 mod 7, the value is 2. 4 mod 7, the value is 4. And 8 mod 7, the value is 1. And 16 mod 7, the value is 2. 32 mod 7, the value is 4. And 64 mod 7, the value is 1. So this indicates that 2 cannot generate all the elements. It can generate only few elements. So this cannot be a primitive root. Okay. So when we are going to consider primitive root, it indicates that it has to generate all the elements in the set. Since when I select the value of a as 2, it is not generating all the elements. So now let me consider a as 3. So now 3 to the power of 1 mod 7 is 3, and 3 square mod 7 is 9. 9 mod 7 is 2, and 3 cube mod 7. So what is 3 cube? So we are going to get 3 cube as 27. 27 mod 7 is 26. So as a result, we are going to get the value as 6. Then what we are having is 3 raised to 4 mod 7. So when we are going to consider the value 3 to the power of 4 mod 7, we are going to get the value as 4 itself. And next, let us consider 3 to the power of 5 mod 7. So 3 to the power of 5 is mod 7 is 5, and 3 to the power of 6 mod 7 is 1. So now we can observe that all the elements, that is 1, 2, 3, 4, 5 and 6, all the elements in the group were generated by the value 3. So this indicates that 3 is the primitive root. Okay. So using 3, I can able to generate all the elements. So now when I am considering the number, so let me write the table. So when I consider the exponents as 1, 2, 3, 4, 5, 6. So these are the exponents I, and the number y, a to the power of 1, that is 3 to the power of 1 is 3, and 3 square is 2, and 3 cube is 6, 3 raised to 4 is 4, 3 raised to 5 is 5, and this is 1. So now here these are the numbers I have obtained by using these exponents, and these exponents are called as discrete logarithm. So for a given number y, the corresponding discrete logarithm, we can write it as, when y is equal to 2, its discrete logarithm is 2. When y is equal to 1, its discrete logarithm is 6. When y is equal to 6, its discrete logarithm is 3. So like this, we can able to consider the discrete logarithm. Okay. So here when the value of n or this modulo or modulus is small, we can easily find out the primitive root and also the discrete logarithm. Suppose if the value of n is very large, okay, so in that case, finding the discrete logarithm is hard. So that is the reason Diffie-Hellman key exchange is using this as a security to share the key. Okay, because in Diffie-Hellman key exchange, what we are going to do is, we will going to consider primitive root to the power of private key. So where this private key is the discrete logarithm. Okay.